Well, we improved the performance in a number of areas. Are there any opportunities left out further to exploit? What about memory accesses? They are so slow. Is there anything we can do there? We can make memory faster. We have reduced memory accesses as much as possible already. So what is left? Aha! Maybe we can parallelize the load stores. In this lesson, we are going to explore reducing the speed gap that perpetually remains between the CPU and the memory. It takes two to tango, that is, every instruction needs two loads to bring the data into the registers. And if they execute one after the other, we'll increase the delay further. How do we reduce it given multi-bank memory architectures? We are going to use parallel accesses to memory banks. Our objective will be to generate parallel load store instructions through compiler optimizations. We need to control the code and data segment growth. So students, we are going to deal in this particular lesson with parallelizing load stores. In other words, how to do them concurrently to the different parts of memory so as to save the access time. And so we are going to begin this lesson with a quiz to test our knowledge of latency here. So here is a quiz on memory access times. In general, how many clock cycles are required to access each one of these memory hierarchies? We have 4 of these here: registers, caches, main memory, and disk. And with your knowledge of computer architectures, please write the number of cycles for each one of these memory hierarchies. Please go ahead and write your answers now. Let us start with the registers that you are most familiar with. The right answer is 1 cycle. Registers are closest to the ALUs, and the operands can be quickly accessed, typically just in 1 cycle from the registers. What about caches? How many cycles it typically takes? So the answer here is 3 cycles. It varies from architecture to architecture, but typically anywhere from 3 to 5 cycles is the right answer here. Let's now go to the main memory. The main memory typically takes a lot longer in terms of access time, and it takes 20 to 100 cycles to fetch the operands from main memory. And last but not least, the disk access typically takes 0.5 to 5 million cycles. It's a huge amount of time it takes to get operands from disks because the disks have to rotate, the tracks have to align, and the operands have to be fetched. All of these takes a long time due to mechanical activities, and that's why it takes a long amount of time to access the values from disk. In modern processors, we have many other kinds of memories that are present there, such as flash memory, non-volatile memories, and so on, and their access times are in between that of a cache and main memory, or that of main memory and disk. So now, having seen the access times of main memory to be from 20 to 100 cycles, the real question is, how can we get these operands for typical instructions as quickly as possible so that we can reduce this access time? One of the approaches to solving these problems is what we call parallelizing load stores, and that is what we are going to focus on in this lesson. So let us look at what the problem is. The problem is this, that how can we merge loads and stores into parallel loads or parallel load stores which execute concurrently and therefore are able to get both of the operands of an instruction as fast as they could from the memory. Now remember, in many of the processors, large amounts of data, especially the array data, is always held in the main memory, and many of the embedded processors just use a scratch pad to temporarily hold some intermediate results and so on. So in many DSP applications, for example, you get the operands which are held in main memory and you try to get them in parallel. The memory is organized in terms of memory banks, typically called as X memory and Y memory. And the idea is to parallelly execute the loads from both of these banks so that the operands are accessed without any more delays. Remember, if we execute the load stores or loads sequentially, let's say we have 2 operands and we try to execute them one after the other, then the latency is going to add up. By doing these parallel loads, we are going to actually get the operands as quickly as we can, and we'll be able to process them in the ALUs. So this is the problem of how to maximally merge loads so that they are most efficient, they are executed in parallel. And the same problem also can be done for one load and one store, and sometimes even two stores. Now let us look at the solutions that were there in place for these particular problems, and then we are going to look at our own solution that we devised here. So one of the solutions was to devise a integer linear programming formulation of this problem. And what they do is they take these different load stores that are scattered all through the program, and then they try to formulate this problem as an integer linear programming problem so that under certain constraints we are able to maximize the number of parallelized load stores. However, later there was another approach which was developed to parallelize these load stores by using a graph modeling of the problem. And the idea here is to hold these load stores and their relationships to each other in terms of a graph and find out which of the load stores could be combined together. So first, let's look at the XY memory architecture to understand how this works and how the parallel load stores execute. So what we have here are two parallel banks in memory called X memory bank and Y memory bank, and each one of them has its own address calculator. In other words, the address calculation for X memory and the address calculation for Y memory can proceed in parallel. Not only they have their own address calculation units, but they also have two different buses here, as you can see, in which the operands can be parallelly fetched and sent to the ALU, and that's how the loads could operate in parallel, or one load and one store could operate in parallel, or two stores could operate in parallel. Now this architecture also imposes certain restrictions. So the opportunity here is, if you are able to put one operand in X memory and the second operand in Y memory, you can parallelly access them in terms of loads or load and a store or two stores. But if both the operands unfortunately end up in the same memory bank, such as both of them end up in X memory or both of them end up in Y memory, then the parallelization opportunity is lost. And therefore, along with these load stores, one of the constraints that we had to obey is the two parts are in two different memories. That is, the operands of two loads, those are in two different memories, or one of the stores and one of the loads, they also reside in two different memories. So now, before we get into the graph-based approach, let's briefly look at how the integer linear programming approach really works. So what we have here is each of the variables ni is to be allocated to one of the memory banks, and we give it a value 0 if it is allocated to bank X, we give it a value 1 if it is allocated to bank Y. And then there is an edge between the two variables which are a part of the same operation. What we do here is, if the two operands are given in two different parts of memory, then we assign a value 1 to indicate whether the instructions are merged. However, if they are allocated to the same memory bank, then we give it a value 0, indicating that those instructions cannot take advantage of these parallel loads. So under these constraints of allocating a variable to one of the banks through 0 or 1, and indicating which of the operations benefit under this assignment, again by giving it a weight 0, 1, we have a nice problem in which we carry out the assignment of variables so as to maximize the total weight that we can take advantage of, or the number of operations or instructions that are covered by this assignment. And so by doing this assignment, our goal is to maximize the objective function, which is the profit for doing this assignment. Note that in this particular formulation, the variable is always assigned to one of the banks. In other words, if a particular variable is given a particular bank, such as X, throughout the program, it stays in that particular bank, it cannot be moved to any other bank. So that is an important thing to note as far as this formulation is concerned. Now let us look at the alternative representation as a graph problem. In this particular representation, each of the load stores is given as a node. Remember, this is not about variables, but it's about individual load store and it's shown as a node. If an edge is present between the nodes, it represents that they can be merged into a parallel load store instruction. And how do we know whether they can be merged or not? They can be merged provided their respective operands are in different memories. And what we do in this particular case is to pick a maximum number of edges that are disjoint to represent that the load stores are merged. Because remember, one load is, if it is merged with another load, it is not available for merging it with some other load. So that is why we pick here the maximum number of edges, but we also make sure that they are incident on different nodes and therefore they are disjoint. So here is a nice visual of these. These may be different nodes which are loads, and here are certain other nodes which represent certain other nodes of loads. And now this node can be merged with this, or this node can be merged with this. Let's say 1 can be merged with 2, and so is 3 can be merged with 2. If 1 and 2 are to be merged, it automatically means that we cannot merge 2 and 3. And that is why we must pick these edges which are disjoint. And our goal is to pick this in a maximal manner in this particular graph, which is bipartite graph, by the way. Now, having seen both of these formulations, integer linear programming versus graph formulation, let us see why graph formulation is a bit more natural to use. Recall your memory on register allocation here, how the register allocators work. So here is a simple program. We have many values being defined here and it's being used in different instructions in the IR. And what we are showing here is the live range of different values. For example, this shows a live range from the first definition to the use of A and so on. And these live ranges start with the first definition and end at the last use. So for example, A's last use was here, so that's why the live range has ended here. B started here in terms of its live range, but then B's last use was over here, so it ended there and so on. So note that these are different live ranges that are being shown through this particular diagram here. And here is the interference graph of these live ranges. As we know, B and A and C overlap and so on, and therefore A and B are overlapping in their live ranges and so on and so forth. B and C are also overlapping, A and C are overlapping. So this is the interference graph which is built out of these different live ranges. Now remember that we have done graph coloring here through register allocation and given all these registers, like for example, A is getting a red register, so is D and E, because none of them are interfering with each other. But A and B have to get different registers, and C and A have to get different registers, and so on. So recall our discussion on graph coloring. After doing register allocation, we have this particular graph which looks like this. Now remember that we have to allocate these loads and stores at the beginning of each one of these ranges. And so we'll have some loads here for the beginning of each of the live ranges. And what this graph is also showing is, since B and A's live ranges are sort of overlapping, there could be a possibility of some loads of A and some loads of B, especially in the beginning of the live range, could be merged here. So the same graph shows us which are the load stores that could be merged for a parallel load store, and that's why the graph formulation comes in handy here. Now remember that sometimes we could even spill a range, that is, A may not get a register, so there will be lots and lots of load stores within that range, whereas B may have only the load at the beginning of his live range, and therefore we could take one of the loads of A and the one of B and we can merge together as a parallel load. which is also indicated by these. In other words, the overlapping live ranges are reflected in the interference graph, and therefore the interference graph also gives us a way to figure out which of the loads could be potentially combined from different live ranges. So in this formulation, the model remains simple and it is using the interference graph, and it can be solved nicely by using this particular representation, and that is why graph-based models are preferred for solving this problem. So in this work, in the paper that we have given to you in the instructor's manual that we are going to read along with these slides, we are going to model the problem using the graphs. First, we are going to identify which of the loads can be merged together, and that is why we call this as movable boundary problem. Now remember, the loads are there in the program at the point of code generation, but some loads could be even moved up or down, and therefore they could be made to overlap with each other even though they are not directly next to each other. And so they could be co-located at the same point or static program point by moving them around, which is essential for parallelizing them. So the first step in this algorithm is to identify which load can be moved where, or which store can be moved where. So we define what is called as motion schedule graph, which says that if I have this load here, I can move it up until this particular point, or I could even move it down until this particular point. And similarly, if I have another load here, I could move this up until this particular point or move it down till that particular point. So you can see that since this load can be moved down and this can be moved up, they could be brought into the same location here and therefore can be used for parallelizing into one parallel load. And that is what is modeled by using this motion schedule graph. The next thing that we do is remember that when the loads could be moved to one location, it doesn't give us automatic guarantee that they can be parallelized. Recall that their operands must be resident in two different banks, and therefore what we'll have to undertake is sometimes putting those operands actively in two different banks, and this is what we call as variable duplication. In other words, if we're trying to merge those two loads, and if one of them has an operand in X and the second one also has an operand in X memory, we'll pick one of the two and we'll make a copy of it into Y memory, and therefore we will load one from X memory and another from Y memory, and in that case the load will become parallelizable. Sometimes we'll be merging these loads and stores across basic blocks, and we'll have to carry out replication of these variables into banks across the basic blocks, and in such cases we'll open up more opportunities for merging the additional stores that we have introduced to move the values, and that is the problem that is to be solved. In other words, look at this example that we had a load here which was from X memory, but now we want this particular operand A in Y memory, so we would put a store here for this operand into the Y memory. Now this additional store can be also merged with something else so that we don't pay the price for this, and such mergers can be carried out across basic blocks. So that was one way to replicate the operands into different memory banks so that we can maximally parallelize the resulting load stores. The other one uses what is called as rematerialization. What is rematerialization? Rematerialization is a technique which is used for recomputing the same operand and storing the value in another bank. So for example, if A were to be computed using B plus C and A were to be in X memory here, but we wanted A's memory image to be in Y memory. So we wanted in fact something like A of staying in Y memory. So how do we do it? Either we copy the value from X memory to Y memory, or if we already have these operands into different memories, we actually recompute that value and store this into the Y memory. So the second approach, which just recomputes it because these operands are already in different memories and stores another image into Y memory, this is called as rematerialization. So what are we rematerializing? We are rematerializing the value of A into Y memory by recomputing it instead of just making a copy of it. How do we recompute it? We already have B and C in two different memories, and therefore their computation of B plus C will be very inexpensive. So that's how we will do, and we'll recompute the value of A and we'll store it in Y memory. So what we have here is what we call as an iterative approach. In other words, we will introduce some additional computations because of rematerialization or because of some additional stores to copy the values from one memory to the other. And then in the next iteration, we'll try to take care of these additional operations by parallelizing them, and therefore we'll eliminate anything that we have added to the program. Otherwise, this approach will not work well. If we take care of some loads by parallelizing them, but on the other hand introduce some other operations which we are not able to parallelize, then the additional operation that we introduce will become a bottleneck, and that is why we have an iterative approach to remove the additional operations that we introduce in the next iteration. Now, having seen the motion graph and the overlapping ranges and so on, these basic concepts of moving the loads and stores around so that they can be co-located, let us understand our knowledge of this through a simple quiz. So here we have a simple program fragment, and the question is, given the following program, check the answers that are true. We first have a store which is going to the address 1 from register R2. So the value is stored in address 1. Following that, we have a load which is loading the value from that address into register R1. And then finally we have an instruction which is taking that value in R1 and assigning it to X. So what we want to know is if these following statements are true with regard to this program or not. The first one asks you, is the load possible to be moved above the store command? In other words, can we move the load up and execute it before the store? The second statement is, the load can be executed after the assignment command of X is equal to R1. Is this true or not? So the first one asks you if this load can be moved earlier than the store. And the second one asks you if this load can be moved after this X is equal to R1 statement. Please go ahead and write your answers now. If you think they are true, put a check mark, otherwise put a cross in these boxes. Let us look at the answers now. The first one asked us, is the load possible to execute above the store? Can it go before the store? And the answer to that is no, it's false. The reason is this: the store has put a new value into this address 1, and the load is then using that value from the memory location and giving it to R1. If we move this load before the store, then we'll be seeing an old value which is not yet stored into the address 1, and therefore we will be violating the semantics of the program. So the first statement is false. Let us look at the second statement now. The load can be executed after the assignment X is equal to R1. Is that true or not? You can see that in this particular case as well, if we push this load down, then we do not have the right value sitting in R1, which can be used in instruction 4, because now we'll have an old value which is sitting in R1 because the load has executed or is moved down, and therefore it will be wrong to move this load down because we need to have the right value in R1 so that we can use it for this particular instruction. So the second one is also false. So you can see here that the load cannot be moved above the store, and it cannot be moved below R1 as well. However, it can lie in between this. It could, for example, go from position 3 to position 2 and so on. So this defines a range for this load where it can be moved. In this particular case, it could be just instruction 2 or 3. That is where the load can actually sit. Now remember, the store itself could have been moved up, in which case this range could expand. So if the store itself moves up, it creates more room for load to go up, or if this instruction can be moved down, that also creates more room for load to move down. And that's the whole idea here, to see how much large room we can create for a given load by moving other things around. So you can see from the previous quiz that what stops the motion of load above the store or below the use is which value is getting defined where and is getting used where. So with regard to that, let us test our knowledge of the definitions and uses and the chains, which will help us clearly figure out where or whether a value can be moved around in the control flow graph or not. So what we have here is the simple program here, which is in terms of a control flow graph and different statements which reside in this control flow graph. We would like you to fill in the DU chains from the definition to the use for each one of these things. For example, we have a definition here for x is equal to 1. Please fill in who all is using this particular definition by writing it over here in terms of its DU chain, or the number of statements or which statements are going to use this definition. Similarly, let's find out which statements are going to use y equal to 2 and so on. Using your knowledge of previous data flow that we have seen, please go ahead and complete this definition and uses in these boxes over here. We're going to go over some of these answers here that we are seeing in terms of who is using this particular definition and the DU chains here. So let us pick, for example, which are the uses that are going to use x is equal to 1. You see that this definition starts here, it goes down here. If the control flow goes this way, this x is going to be the one which is using this x is equal to 1, and so is this other one. So number 4 is the first use that takes advantage of this definition, which uses this particular value equal to 1. And in similar ways, you can see that we could go from here to here, follow this control flow, go in this particular way, and we could eventually go to statement number 9, and this x, which is in statement number 9, could also use this x is equal to 1. So when do we say that there is a DU chain between one particular definition and its use? If the definition manages to reach that use along one path, then potentially that definition could be used by that use, and therefore we have the second use here as equal to 9. Remember that if we, on the other hand, take this particular control path, go and here x is redefined, you can see that if we keep going down this particular path, we won't be able to use this x, which is sitting as x equal to 1. But that's not the point. As long as there is a path along which we can carry this x around and can deliver it to that x, then that definition is being used over here. So along the second path, this x is of course not getting anywhere further because there is a new x coming in here, and therefore along this path, this x does not reach this particular point. However, the x does reach along this particular path, and therefore this is reaching that point, and therefore there is a DU chain between 1 and 9. Similarly, let's look at the DU chain for statement number 2. What is going on here is y is starting here, and we could go down here, and we could keep going down here, and finally we could go here. So along this particular path, y just falls down all the way here, and it can use this particular y value from over here, and therefore number 7 could use the value from number 2. That's one thing. And second path for this value to go and deliver it could be like this. This y could start here, goes here, then it goes here down, it goes here, and instead of going down here, it comes around like this and goes to this particular y. So because there is a control flow for y going down like this, over here finally, and then going around this edge, and it can deliver this value to that y. The second use point of this y is at statement 9, and that's why we have that also in the DU chain. Similarly, we can work out the others. I encourage you to work out these by following this reasoning. Again, what we do is, if there is one path along which we can take the value and deliver to a use, there is a DU chain between those 2 points. Keep that in mind and fill in the rest of the stuff here. Let us first talk about the memory access instructions. So we could have a store going to a particular address which is located here, or we could have a load from a particular address located there. Typical instructions that we encounter, especially for DSP codes for which we are interested in doing this parallelization, is base plus offset. So in other words, there is a pointer address for the starting of an array, and then there is an offset which offsets the address to a given element, and therefore by using these 2 pieces of information, we can figure out if there is a potential collision between the load and store. So for example, if the base addresses that the load and store are using happen to be 2 different ones as shown over here, then there is no collision because it is accessing 2 different arrays because of the 2 different base addresses. So base B1 refers to one array, base B2 refers to another array, so therefore there will not be any collision in the addresses of these 2. However, if we have the same address, let's say B1, being used by both load and store instructions, but they differ in terms of their offsets. One of them is using an offset of some value which is 20, the second one is using an offset of a value 30, then we again know that these 2 are corresponding to 2 different elements of this array, and again in this particular case there is no conflict. However, many times at compile time we do not have this knowledge, so we have a situation in which both load and store access the same base address, and the offset is there in terms of some unknown which is I for one instruction, and another one which is in terms of j for another instruction. So let's say this is one of the loads, this is another store. So the question is whether they should conflict or not. Here we have to make a conservative assumption that I might be equal to j, and therefore this load and store might be doing the same memory location, and therefore we must say that there is a conflict here. So many times we can figure out there is no conflict if the offsets are 2 different, or if the base addresses are 2 different ones referring to 2 different arrays. But in some other cases, if it's the same array because of the same base address and 2 offsets are unknown, one being I and second is j, then they have to be assumed to be equal in the worst case, and therefore we have to assume a conflict here. Now this is called as the memory access oriented alias analysis, which we do as the first step. At the end of this step, we will classify if the 2 accesses are conflicting, potentially conflicting, or are definitely not conflicting, such as in these examples. In such cases, this load and that store could be moved across each other, and in this case as well, these 2 loads and stores can move across each other, but in this case they cannot because they could potentially violate the program semantics. And remember what has happened prior to this, the register allocation has already taken place, the load stores are in place. So remember that we have webs here, that is the variables which share the DU chains are all been allocated onto the same register, and even if the variable name might be the same, if it is in different webs as we saw earlier in the register allocation, it can be put in totally different memory locations. That is, a variable is considered as one unit as long as it is in one web. Different variables for different webs are considered as totally separate from each other. This is what we call as value separation. So for example, this x is feeding to this particular x. This could be one web, but the other x, which is feeding to yet another one, is considered totally separately. So these 2 are 2 separate webs here, and therefore they could be put into totally different locations. And this concept is called as value separation that we saw earlier. Now why is this important? This is important because that way we can separate the load stores for these 2 webs, and the webs define what load stores exist in what part of the program. Now let us look at yet another important basic concept, which is motion range determination. What is a motion range determination and why is it important? Remember, we are trying to move the load stores between different intervals, and we have seen a simple example which limits the range of motion for a load some time back. So the interval between the program points where a load store can be legally moved is restrained by the dependencies, and that restricts what we call as the motion range of a given load or a store. For example, consider this load. There could be a store which could block its upward movement, and there could be use of this value R1 which could block its downward movement, and so this range is called as the motion range of this load. Now remember, this is also dependent on this store and this use of R1. So if this itself can be moved down, we can increase the motion range, and if this can be moved up, we can again increase the motion range in the upward direction. So the key idea here is that the load store instructions which have overlapping ranges, they may be merged provided we can satisfy some other constraints, such as their operands being in two different banks. And the range of motion for a given load store depends on other load stores and uses of the loaded register, and that's why we formulate this problem as a movable boundary problem, which says that a given load depends on the motion of another store and so on. So students, we are looking at movable boundary problem. What it means is we have certain load stores which are there in the original program, and we are trying to move the load stores around so that they can be merged maximally. But the problem is that the motion of load stores depends on other load stores, and that is why we call this as a movable boundary problem. Let us illustrate it by using this simple example over here. So what we have in the original program is we have two stores, one going to address 2 and second one going to address 1 from the registers R1 and R2 respectively. And later in the program, we have a load coming from address 1, which is loading the value in R1. Now we want to move this load so that it can be coupled with certain stores and we can generate parallel load store instructions. If we do it in this particular way, that we want to couple the load with this particular store and we move it in this particular fashion here as shown in B, what happens here is it will allow us to do the parallelization, because now this load and store can be one instruction. But as you can see here, we are moving this load above the store. So in other words, in the original program, it is going to load a value which is modified and put in there by this particular store. It is loading that value from that location into R1. But in this program, it is loading an old value from the address because the store is sitting below it. So in other words, if we had to move the load up, we have to make sure that the store stays above this particular load so that it is legal, and that is called as the movable boundary problem. So the motion of this particular load up really depends on the store, which I have circled here, and this store has to be above this particular load, because otherwise this load will get a wrong value from the address 1 and it will be an illegal program. Now we can of course push this store as up as possible, and that will create a motion for this load going up, and that is what we do when we try to solve this problem. So what is a movable boundary problem then? The motion boundary of one load store instruction is another load store instruction, and we have an ordering between the load stores. So in case we move one load store somewhere, it affects where the other load store could be moved. This particular problem is called as movable boundary problem. There are more details of this in the instructor's reference guide in the paper that is assigned for reading. And in other words, assuming fixed boundaries will cause an incorrect merge of the program, because we are trying to move the load store simultaneously here, and if we do not account for the motion of one load which also affects the store and vice versa, it will create an incorrect semantics. So how do we solve this particular problem or movable boundary in which one load store affects the motion of the other? So we call this as pseudo-fixed boundary. In other words, we call this as a fence. When the fence moves, the other load store which depends on this fence also can move. And since the stores affect the upward motion of loads, what we want to do is move these stores as early as possible so that we can create a longer range for the motion of the dependent loads. This store, for example, is putting something in a memory location, and there is another load which is reading the value from that memory location. So naturally, if this load has to move up, this store has to move up. And that is why the store is moved as early as possible in this particular scenario. Now the second one deals with the motion of the load. What we want to do here is move the load as late as possible so that the motion of the store is in fact held as long as possible. So imagine this particular load which is reading a value from a particular location again, and again this store which is putting a value into certain location. If we have to move this store much longer than the range currently it has, we have to push this load down so that the store can be moved above it. In other words, the ordering has to be that the store executes first, then the load. So in case we want the store to have a longer range, we have to move the load down. And that is why for the load to increase the store's range, we move it as late as possible. So now let us see how we can build a motion schedule graph based on these movable boundaries. So what we have here is a web first, which is representing all the load stores corresponding to that web from the memory. And then inside this web, we have individual nodes, which are the load stores corresponding to that web. So these are, maybe this is a load, this is a store, and so on. And we have one web here, and we have another web here. Similarly, having its own load stores as shown over here. So let's say this is a variable u, and this is a variable v. And these are load stores for v, and these are load stores for u. So now we have edges which represent the ones which can be overlapped and which can be combined together between these two webs. So let's say this particular load over here and that load from v and from u can be combined together. So there is an edge here. Let's say the store from u can be combined with a load from v. So there is another edge here. So in such a way, we can build a representation of which load stores of which webs can be merged together. How do we decide that? Because they can be moved using the motion schedule graph, and they can be co-located at the same code location. If that is the case, then there is an edge between the corresponding loads, or between a store and a load, or between two loads, and so on. So in other words, to summarize, the individual nodes represent the load stores for a particular web. The oval that surrounds the load stores represent the variable which has those load stores spread across the program points, such as this is a web u, and these are its load stores. And finally, the edges link nodes that have overlapping motion ranges and which can be potentially merged, such as over here, this is another web, and if we have an edge between these two nodes, then this load and this load can be merged. This is for u and this is for v. Okay, let's do a quiz on the motion range determination. That's an important concept that we had seen in terms of how much we can move these load stores to be able to combine with the other load stores. We have shown to you here one sample. This is a sequence of stores and moves and loads which uses different registers which access different parts of memory. With regard to these, we have shown that the motion range for 1 is going from 1 to 3 because of the register dependency. We cannot push this below this because the register R1 is conflicting with R1 here. So this particular range can only be moved till the point of this particular R1. So we can put these instructions anywhere in between this range, but we cannot push it after R1. And that's the way we would like to do this motion range determination. So for each of these instructions, such as number 2, number 3, number 4, assuming other instructions are fixed, try to determine such ranges. Please go ahead and mark your answers here. And what we have here is a nice motion range graph which is shown over here, which explains what is going on, and the actual answers here. For example, for instruction 2, we can have it here, or we can move it down all the way till here because of, again, the conflict that we run into R3 over here. So this is its range, starting from here to go down. And similarly, for D, we can push it down all the way till here, but there is a conflict between this instruction and that's why we cannot push it beyond this. So in some sense, the other instructions act as stopping points for motion of some of these instructions, and that determines these ranges. So doing this particular exercise, here are the answers which are shown for each one of these ranges. For others, you can easily see it from this particular solution that is shown here. So for example, for 9, we could move this load all the way up to this particular instruction 6, but not above it because it is conflicting on register R2. So please go ahead and check your answers using this motion range, which is shown over here. So let us now take a look at the overall phases of this approach in terms of what all the information that we need to find out and how do we use it for carrying out the maximal generation of parallel load stores. As we have looked at in the previous few slides, we first start with determining the range of motion. And then the first thing that we try to do is we merge those ranges without replicating variables or instructions. The next thing that we do is load store replication. In other words, we can put the load stores across basic blocks and we can create more opportunities for motion across basic blocks, and we are going to look at some of these in the next few slides. After that, we eliminate certain conflicts, especially some registers could be in use in those basic blocks, and when we move some other load stores, we might create some issues there. We get rid of those. And then we carried out a merge for these newly moved instructions. So you can see that this particular framework is repetitive or iterative. That is, we carry out certain motion of load stores across basic blocks, replication, we carry out this optimization, and that might open new opportunities, and we keep doing that. That is why we have an iteration here. Once we have done that, and after we exhaust all these opportunities of replicating the load stores, we look at newer opportunities for duplicating the variables. Remember, in the beginning of the lecture, we looked at how certain opportunities could become available if the variable were to be present in both X and Y banks, and that is where this particular phase comes into picture. So in this phase, we take a variable, and let's say we have a load of a particular instruction, but that variable is present in an X memory, and we have another load which is also present nearby, which can be merged with it. Unfortunately, that variable is also in the X memory. We cannot then merge these two together. So in such a case, what we could do is we could replicate the variable, and we could now load a new value out of a Y bank where that can be now merged with this load. So since this variable is now being loaded out of Y bank and the other one is being loaded out of X bank, now we can merge these two together, and that's the goal of variable duplication. Similarly, we keep doing this, and it could open certain other opportunities, and we keep iterating and exploiting those. And then finally, the interplay between load store replication and variable duplication, we again iterate and we take advantage of more opportunities. So what we have here is these points which are marked A, B, C. What they tell us is what is the effect of each one of these phases. In other words, how much we can merge without carrying out any of these optimizations which are in the box. Then if we just carry out load store replication, how many more we can do, that's shown at point B. And then finally, if we do variable duplication and do all the optimizations, how many opportunities become available overall. That is what we look at in this point C. So now let us look at how we carry this load store replication across basic blocks. So first and foremost, we would like to move this load store only when the reference is live. In other words, if the reference is not live, moving a load store in that particular area is going to enlarge the live range, and it's not going to be profitable because it will create additional register pressure and that will cause more spills. So now, staying within the live range, what we do is we move the stores using the extended basic blocks, and we are going to look at some of these examples in next few slides. We do the loads, we move the loads on reverse extended basic blocks. Again, we'll look at the examples there. So the condition that is important to be observed while moving this or replicating these load stores is that if we move these load stores onto the other basic blocks, one should be able to combine them with something else. Otherwise, it's not profitable. Now let us look at the cross basic block move through a simple example. What we have here is three basic blocks here. The first basic block has a store. The basic block number 3 has a load, and basic block number 2 does not have either a load or store. Now you can see that we cannot merge this store and this particular load because they are in two different basic blocks. So what we will do is we will replicate this particular load and put a copy of this load in this block, and we'll take this load and we'll also put its copy in the predecessor block. So now you can see that we don't need this load anymore here, and we'll have a copy of this load over here and we'll have a copy over there. You can also now see that we have a store here, and then we will have a copy of this load over here, and these two things, the copy of this load which is made here and this store, now together they can be merged into a parallel load store. And on this particular path, of course, we do not have any opportunity to merge this load with anything else, so the load will stay as a non-parallel load on this path. Thus, by replicating the load in a reverse EBB sense, this is by the way reverse EBB here, extended basic block, we are able to create a parallel load store here and just leave the load as it is on this side. Now let us look at an example of variable duplication. So that was an earlier example of instruction duplication. Now we can see how replicating variables across banks helps to parallelize more load stores. Let us now take a look at this variable duplication example. Originally what we have here is that the variable A is residing in only one of the banks, and that is precluding the opportunities for parallelization. So initially we do not have this store going into Y bank, we just have a store going into X bank, and so this variable B is also in the X bank, this store is also in the X bank, and that prevents parallelization here because remember the operands must be in two different banks. So if B is in X bank and so is A, that's going to prevent parallelization. Not only the parallelization is prevented here because A happened to be in the X bank, and then we had this particular store, and let's assume that D is in the X bank as well, and so is D, and therefore they could not be parallelized together either. And thirdly, we had a store here which is for C in this particular basic block which is going to X bank, and initially we had a load from the X bank as well. So let's say this particular one was not really A of Y, but it was A of X, that is loading the version of X which is in X bank. So because of which this is in X bank, so is this, and therefore there was no parallelization possible here as well. So you can see that several parallelization opportunities were not possible because all these variables, B was in X bank, A was in also X bank, C was also in X bank, and therefore the corresponding load stores could not be parallelized. But now see what we did. So now what we did was we added a store of A to the Y bank over here, and what has happened now is A could be found not only in X bank, it could also be found in Y bank. Now you can see that B is in X bank and A is being stored in Y bank, so we could parallelize this load store together. We inserted another store here for storing the value in Y bank over here, as you can see. And now we have these two stores, one going to X, second is to Y. They could also be parallelized. And now, focusing on this load, which was coming out of the X bank earlier, remember A was only in X bank. Now A is also found in Y bank. So we decided to convert this load to come out of the Y bank. This C was always in X bank. And since now A is in Y bank and C is in X bank, we were able to parallelize this as well. Finally, if you go to this basic block, D was in X bank, but now we have a choice of using A from either X bank or Y bank, and we decided to convert that original load from X bank to the one coming from Y bank here, and because of which this is also parallelized. So you can see that by replicating A through this store over here and through that store over there, we have created opportunities which gives us choices of loading A either from the X bank or from the Y bank. And since the other operands were in X bank, we decided to load those out of Y banks and parallelized these load stores here. So this shows an importance of carrying out replication of variables and the additional instructions that are needed to carry out the replication. Many times they could be absorbed without any cost because they themselves could be coupled and be parallelized, as shown in this example for stores and coupling of this load with this store. Now we mentioned earlier that after carrying out this instruction replication or the replication of the operands into two different banks, we need to worry about conflict resolution or conflict elimination. Let us look at these in terms of simple examples. So one of the reasons the conflict may occur after replicating the load stores is that now we are entering some loads or stores in the live ranges of other variables, and because of this, those registers might be preoccupied with some other operands at the point where these load stores are replicated. Now, this could lead to register conflicts, and therefore we might have to redo register allocation when the load stores are replicated. Some other reasons for resolution of these register conflicts is that, remember that when we generate parallel load stores, there should be certain restrictions on the registers. For example, the store and load cannot share the same register. And so because of this reason, even though it may be possible to parallelize the store and the load, one has to make sure that they are going to two different registers. And because of this reason, we'll have to again do some conflict resolution. For example, if this load is happening here when replicated from a particular memory location into register R1, whereas this particular location also was storing this register R1 into some other location. Let's say this was going to Y memory, this was coming from X memory. So perfectly possible to parallelize these two because both operands are in different memories. However, you can see that the register names are common, and so one of the ranges will have to be reassigned to a different register to avoid this particular restriction on parallel load stores. What is the restriction here? The registers that participate in a parallel instruction, the load and store parts, they have to be disjointed. So how is it then done, the conflict resolution? What we will do is we'll have to free a register somehow, and then we'll have to reconstruct whatever was in it at a later point. So let's say in this particular case, we want to get this R1 to occupy some other value. If we have to free whatever is there in that R1, let's say R1 was containing something like A which was equal to B plus C. So A is being contained in R1 here. And so if we are freeing the register here R1 from A, we will have to reconstruct the value of A in R1 after we do this parallel load store. How do we do it? We'll just recompute it as B plus C and generate that value in R1. This technique is called as rematerialization. What is being rematerialized here? We are recomputing or rematerializing the value of A into R1 by computing it from B and C, its constituents. Now, having seen the overall framework, how it works, what are the different things that are going on there, let's look at the results here in terms of what is going on different benchmarks in terms of the compilation time. So compilation time is important here because this optimization is doing many different things, and what we want to see is if that has any implications on too much time being taken to perform this analysis and so on. So here are the different benchmarks on which this framework executes, and here are the different timings for that. And we have the original compilation time and the compilation time being measured at different points, which we mentioned earlier, point A, point B, point C, and so on. And then we have an overall percentage improvement or percentage increase in the compilation time. You can see that by doing very aggressive optimizations, we are just increasing the compilation time by almost 12%, and that's not a significant factor. And if we remove certain optimizations and keep the compilation framework simpler, in fact, the compilation time does not go up. So the real benefit of doing this optimization is in terms of savings in performance and execution time. So here is the speed up over the original benchmarks. These are very large benchmarks which were compiled by using this framework on the Motorola DSP, which has XY memory, and refer to the instructor's manual in the instructor's reference guide, the paper. You can see that the framework improved on an average 17% execution time by carrying out these optimizations. Here are some more results. Now what we are comparing here is the code size. Remember, we are replicating the operands, we are replicating the instructions, and the code growth, the additional number of instructions, is definitely very important for embedded systems, whether or not we are increasing a lot of code size. So you can see that we have two types of measurements here. One is just by replicating instruction, and then second one is by replicating the variables as well after the instructions are replicated. So if we just replicate the instructions without replicating the operands in different memories, the code growth is just 6%. However, if we do both, that is, if we replicate the variables as well as the instructions, the code growth can go up to 14%. So in other words, the code could become bigger, but of course the performance could also be better. And in the earlier case, the code is just becoming bigger by 6%, whereas if we do full scale optimization, it could become bigger by 14%. So here is the final result. What it shows us is if we do a profile driven optimization, what is the speed up here after doing these different optimizations, and the results are shown over here. And the same results are now shown in terms of the execution time, performance. So what is this profile driven optimization? The profile driven optimization selects only the hot basic blocks where to do the load store merging or parallelization. So we don't do this globally, but we just focus on those blocks. If we do it, then it gives us 16% speed up by doing this optimization. And the code size comparison, if we do it in a profile driven manner, then the code size overall could go up as 12% because of replication only on the hot blocks. You can see that we have managed to decrease the code size explosion by about 2% here. Earlier it was 14%, now it is 12%. And that was our final result. So to conclude, what is the takeaway from this particular lesson? The conclusion is this, that we have a framework here which tries to either replicate instructions or tries to replicate variables or do both. And on interesting architectures, especially the DSPs, the DSP embedded processors, the two operands must reside in two different memory banks, and then they can be fetched in parallel, and that way we have very fast code executing without waiting for one load to be completed after the other in a sequential sense. We can do them in parallel. Not only we have a faster code, we many times also have a much compact code because now the load stores could get rid of additional instructions. And by doing these different types of optimization, replicating the instructions or replicating the variables or doing both, we can gain significant performance by doing this optimization. Of course, the optimization also costs code size increase. So the optimization here is not really geared towards reduction in code size, but is really geared towards increasing the performance, because the parallel load stores cut down the latency. The performance improvement could be quite large. It could be about 14%, and that's a substantial speed up one could get. And so this lesson tells us that many times if you give up a little bit of code size, if you degrade it, you can gain significant performance gain, like 14% in this case. In this lesson, we saw a framework to analyze and merge load stores as maximally as possible. Our heuristic approach led to less compilation time and less code growth and data segment growth. The generated code quality is superior to the exhaustive methods previously proposed. The profile-driven approaches yield even more improvements. So what is the takeaway? By controlling code growth and data segment growth, we are able to achieve maximal load store parallelization.